Well, thank you. Thank you for the opportunity. So I'll be talking about spin qubits that we are working on in Quobly and how we plan to industrialize them. So that's the title of the talk. So I will present Quobly in a few slides. I will then talk about the FDSOI technology on which we are implementing our spin qubits. Then I'll spend some time about this important task, which is mine in the company, to go from research to industry. And I'll show you some highlights of on this topic. So Quobly has been spin-off from CLAT about 2 years ago, just shy from 2 years ago. We have funded ourselves in order to fund this project for a few years, and we gathered a team through direct hiring and also through collaborations. Diversity and quality of life is also an important part of this project, and we'll spend most of this slide on the last part of this with this two tier 1 fab that is so important to the industrialization of spin qubits. So let's start with our technology. So we are making spin qubits onto FDSOI. And the ambition of the company is here. It's to make a full universal quantum server based on these spin qubits that we do on a chip made on the FDSOI technology. Our journey will be long. If you look at the technology roadmap that we have, it spans over more than 10 years to go to a large-scale quantum computer. And to get there, there is 2 important milestones that we have on our way. One will be to have a chip with 100 qubits, physical qubits. And the second one, the second star, is when we will have 100 logical qubits. So that's many more physical qubits for sure. And to deliver this, we have to develop and transfer to the industry a couple of solutions. We have the first one on the left that are already available. So qubits arranged in 1D configuration. So 1 qubit can interact with the 2 neighbors. And we also have the cryoelectronics to pilot these qubits. We can put them in a system in package to have those 2 together in a cryostat. And then we will need to work on co-integrating those 2 aspects into 1 chip. We also will need to develop the 2D array of these qubits, so we improve the connectivity of qubits, going to 2 neighbors to 4 neighbors, and multi-core chips, and quantum links long distance. And with all this, we'll get to this large-scale quantum computer. So, in doing so, the difficulty is not really, the difficulty will be to make the qubit out of a silicon technology. Then we will rely on 6 decades of investments of work in the semiconductor industry in order to solve the scaling issues. And they will not solve this scaling issue because they already know how to make qubits, but because all this big investment of these 6 decades created the skills and the methodology in order to make a yielding technology out of a new module. And that's what we are seeking in going to semiconductor industry for that. So, as I said, silicon spin qubits are known to work. On this slide, you can see on the left a work that has been done in Sego Taoxia lab, that which, by the way, is on the scientific advisory board of the company, certainly because of this. And you can see this very impressive number about fidelity that you can get with silicon spin qubit. And this is one qubit gate, 2 qubit gates with more than 3 nines fidelity. And on the right, that's all the technological work that has been done in CLAT prior to Quobly spin-off that Maud, our CEO, is bringing with us. So how do we plan to make this scaling of qubits? This is this team that should do that, and that was hired exactly for that. This is especially my job to be successful on the industrialization of qubit, and this is with the skills of this 60 plus years of experience in delivering a high yield semiconductor industry, illustrated here in a graph where you see the typical methodology of the semiconductor industry. You take a KPI and then you measure and you reduce the variability of these specific things. So we start from that. So this is what we have in research today, and we need to industrialize. So one can recognize things that are very close to a transistor. This is the red parts that are gates that you will find in transistor. So these are things that you will easily find in the semiconductor industry. Also the source and drain on the side. They will look like exactly the same in transistor and in qubits. And you see some modules that are not present in transistor. This is, for example, the brownish contact here. This is something that needs to be added on top of the transistor technology in order to do a qubit. And the last part is probably the most complex, is we will also optimize this device that we will make for a physics that is not the one for transistor. So you can imagine that the whole 6 decades of work have been used in order to improve anything you need to improve to make a good transistor. If one part of this is not covered in order to make a good qubit, then we will need to work on that one and improve material, for example. So here I use this slide to show you all the knowledge we have in order to do this task of industrialization. It has been over more than 10 years of work in CLAT, yielding all these different generation of devices that you see on the slides. And this is the result of investments that are over 15 million of euro. So now let's talk about this industrialization of the process. So the model is here. The model is here, and we have already the first generation of our technology that has been developed in the research. And we are in the process of redeveloping it into a foundry. I'm saying redeveloping and not transferring because it's not the same tool, it's not the same recipe that we have access to, and everybody knows by working in a clean room that if you don't have exactly the same tools, you're not talking about transfer. You have to redevelop things. And this is where all the knowledge of what makes a good qubit is so important in this task. And we will make chips, QPU, out of this technology in the foundry. And we are at the same time working on the next generation. So illustrated by this 2D array that I presented on the roadmap. We need the whole supply chain of the chip to be industrialized, and what I'm showing here is, and I want especially to focus on the first one, is the industrialization of the substrate to make these chips. You might know that in order to make good silicon qubits, we need to have a very special silicon purified on the isotope 28. So it is especially important to have our partner, Orano, Soitec, and Air Liquide working in making this not once, but in an industrial supply chain. So we can rely on the wafer we need for this production. This is underway. we were talking about FDSOI technology, and what's important is we first leverage and we stand on shoulder of a giant, I would say, because there is this huge investment of more than 400 million euro in order to have this technology available. And not only the technology, also the skills and all the experience that this team have acquired in order to make this technology. And this is what we are going to leverage in order to make good qubits. Good qubits as a new module for this technology. As I say in the middle, the qubit will be a module that will still be compliant or compatible with the rest of the technology. So it's not a long qualification to make qubits out of these clean rooms. And we need to make choices that will lead to a very fast qualification of the qubit module. And this should, at the end, give us, as transistors are very cheap, you know that, cost-efficient qubits, and a large amount of them. And the figure that we need to take out is we need to change less than 10% of the technology in order to achieve all this. The last part of this now is what we've been doing with our tier one foundry partner in order to show this industrialization. So I can share with you today two things. One is a work that has been published last week at SciQ by Giselle, and where you see that we have quantum dots and coupling quantum dots out of the 22 FDX technology from Global Foundry. So this is the best in performance result that we've seen so far out of a foundry. And it is important in those graphs to note that we have the premise of the 1 qubit gate and the 2 qubit gate present in this results in different configuration, as you can see on the left of these slides, where consecutive gates or facing gates show the same quality of results. The second part I'd like to share with you to illustrate this industrialization work is this. So this one is even published this week in ESDERC, yes, in ESDERC, and this is a work done on the technology from ST, the 28 FDSOI, where we have collaborated and in doing co-integration of quantum dots and cryoelectronic, and showing that you can multiplex the readout of the signal of these two qubits, of these two quantum dots. So this is published this week. And with that, I'd like to leave you with the takeaway. So what's important is that we have the knowledge from all the Leti work of what we need to change in a process in order to make good qubits out of semiconductor technology. And we believe that these good qubits will be the result of a lot of work on the quality of the material and on the quality of the process used for this for making them. Then we are doing everything we need to do in our ecosystem in order to make a supply chain that will make this technology a reality. And then I show you two examples of this industrialization is going on in Quobly right now. So with that, nice picture of our offices right now, and I thank you very much.